Hi, it's Moser with a brief tutorial on using the blocks of the periodic table to predict the properties of elements, or getting around the block. When you finish this video, you should be able to identify the blocks of the periodic table and how to use the block location of an element to predict properties based on the electron configuration, which, oh yeah, you can use the block identity of the element to predict. So you already need to know how to write electron configuration in the three basic formats, the difference between shells and subshells and orbitals, and how to use the group and period of any element to write its electron configuration. Let's go. Grab a periodic table out of the special folder for this video. You can go ahead and pause the video. Okay, so you should be looking at this side of the Van Brainer periodic table, and you already know that our periods are the rows, and I've got these numbered down the side, 1, 2, 3, 4, 5, 6, 7, etc. And the groups are the vertical columns, group 1, group 2, group 3, 4, 5, 6, 7, 8, etc., over to 13, 14, 15, 16, 17, and 18. Once we've got that all established, good. If you want to write those down on your periodic table, you're more than welcome to. Now, you recall from the last video you watched that there are some tricks to figuring out the highest main occupied energy level, as well as how the electron configuration of every element ends based on its location in the periodic table. Well, in fact, the periodic table is coded into blocks based on the sublevels that are being filled. Group 1 and 2 are referred to as the S block, groups 13 through 17 are the P block, 3 through 12 are the D block, and the lanthanide and actinide series, remember those down at the bottom, weird ones? Those are the F block. This is a little view of the sublevel blocks of the periodic table, sort of broken apart and exploded. And here's group 1 and 2. That's the S block. Here's groups 13 through 17, the P block. Groups 3 through 12 are the D block, and then what the heck groups are these things? The F block. Goodness, I don't really get it. Okay, well, yeah, you will. Don't worry. Here's an expanded view, and you're going to see really quickly why this is so important. Once you've seen the periodic table this way, you'll never be able to unsee it. A couple quick notes before we delve into all the characteristics of the various blocks. There are two elements which are sort of special cases, and they're special because they're the original elements, hydrogen and helium. The first atoms that would have formed after the Big Bang as protons were forming and neutrons were forming would have been hydrogen, which is, of course, right here, and generally consists of a single proton with a single electron, and helium, which is what you get when you smash two hydrogens together in a sun. So hydrogen is placed in group 1, and if you think about it, what does hydrogen have for an electron configuration? 1s1. Well, everything in group 1 ends in s1, as you remember, but it doesn't behave like the rest of group 1. We'll talk more about why that is later. Helium, on the other hand, is placed with the noble gases, group 18, based on its characteristics, because, of course, it's got a full upper valence shell, but it doesn't share the electron configuration of the rest of group 18 because it's got a 1s2 configuration, which we generally see something ending in s2 in group 2. Nonetheless, we consider helium a noble gas because it behaves like one. So they're kind of weird, but we give them a pass because, hey, they're really old. Okay, time to get out your periodic table. You're going to actually do some coloring. Woohoo! Go get 4 colored pencils. Any colors you choose. And the first thing you're going to do is outline the S block, groups 1 and 2. And you can make whatever sort of little key you would like on your periodic table that will help you remember that the S block is colored, well, whatever color you chose to color it. Now let's talk about the S block. The S block are reactive metals. Now these aren't even things that when we look at them we would think of as metals, but they're incredibly reactive. As a matter of fact, they're so reactive they can't be by themselves. They're never found free in nature. They're only found in compounds because, really, seriously, they can't be alone. The number of electrons in the highest occupied main energy level, also known as the number of valence electrons, is the same as the group number. So, group 1 has 1 valence electron. Group 2 has, oh, you guessed it, 2 valence electrons. Well, that's pretty easy. Okay, pick your next color, because you're going to color the P block. And the P block starts with group 13, runs all the way over to group 18, and we're going to kind of disregard this second showing of hydrogen there. You kind of understand it's because hydrogen's a little strange, but anyway, color your P block. Now, let's talk about the P block. It's groups 13 through 18, as we said, and when we look at the P block and the S block together, we refer to them as the main group elements. Now, the number of electrons in the highest occupied level, in other words, the what? Oh yeah, valence electrons, equals the group number minus 10. So what does that mean? Well, for group 13, they have 13 minus 10, 3 valence electrons. Group 15 has 5 valence electrons. Oh yeah, that would mean group 18. Group 18 would have, 8 valence electrons. Yeah, we've been talking about that whole octet rule. That's handy. You know that group 18, the noble gases, are stable because they have a full outer S and P sublevel. We added that in. Beyond those generalizations, the properties in the P block vary pretty tremendously. After all, the P block encompasses every single nonmetal in the periodic table, well, except for that weirdo hydrogen. It's got all the metalloids, which are the elements that have characteristics of both metals and nonmetals. It's got the halogens, which are the most reactive nonmetals known, chlorine and bromine and fluorine and iodine, really crazy reactive stuff. And lest we forget, the P block includes the noble gases, which are completely unreactive. Okay, so we've got the S, we've got the P. We have some rules for each. Get another color because we've got the D block. Ah, the D block. These are the things that when any mortal human would look at them, they would immediately think, ooh, that's a metal. So the D block elements are groups 3 through 12, and they're so called because they're filling in the D subshells. They're also called the transition metals, and this is where things start to get a little bit weird, because we have those nice, neat, orderly patterns that we've all learned courtesy of the subshell filling diagram. But as we get into the D block, we start to have those overlaps that we are able to predict because of the subshell filling diagram, and the electrons start to do some pretty strange things. But the sum of the outer S and D electrons is equal to the group number. You don't need to memorize that. It's going to become apparent to you soon. The D block is also called the transition metals. They're good conductors, they're hard, they're lustrous, that means shiny, and they're less reactive than alkali and alkali earth metals, that'd be group 1 and group 2 respectively. Some of these metals are actually found free in nature, and some are so non-reactive they can be used inside the human body, where they're going to come in contact with all sorts of, well, just crazy stuff. But let's do a little refresher on why these are called the S and the P and the D block. Well, when we looked at the expected electron configuration for each group, we found that everything in group 1 was going to end with NS1, where N is the uppermost main energy level, that everything in group 2 was going to end with NS2. So hence, these are filling in S subshells. It's the S block. Likewise, when we looked at the P block, we found that everything in group 13 was going to end with NS2, NP1, NS2, NP2, NS2, NP3, blah, 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 until we get over to group 18, where we find that everything ends, well, okay, except helium, with NS2, NP6. So, hence, it's the P block. So, if you remember this handy dandy little drawing right there. When we go from, let's say argon, which ends on a 3p6, and we go to potassium, which will end then with a 4s1, 4s2, what fills after 4s? 3d. So right here is where we start adding electrons in d subshells. Hence why this is the D block. Oh, okay, that all makes sense. Wait a minute. The F block, hold it. The F block are actually filling those 4f and 5f orbitals. This is what happens after we filled 6s. We go to 4f and we fill 4f, 5d, 6p, 7s, and then 5f. Oh, okay. It's the lanthanide and actinide series. And they're pretty reactive. They're pretty big. Lanthanides are similar in reactivity to the alkali earth metals. That's group 2. And the actinides, those puppies are all radioactive. Their nuclei are so large that they spontaneously break apart and emit radiation. Up to now, we've been looking at this version of the periodic table, in which that lanthanide and actinide series have been neatly tucked under the main table to save space. This is going to change your life. Check this out. It's what we call the expanded or long-form periodic table. So let's see, filling S1, S2, P1, P2, blah, 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 D1, D2, blah, 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 until we get down to here and we go, 6s1, 6s2, oh my gosh. Yes, that's right. After we fill barium with a 6s2, we go to 4f. And here's where we start filling in the f's. Wow, that's cool. Remember how the d's are always lagging, so we fill 4s and then 3d, and then 4p, 5s, 4d? Well, the f's are actually filling 2 orbitals behind, and you'll notice that we go from 6s to 4f, and 7s to 5f. Whoa, how cool is that? Periodic tables handle this pull-out, which we usually use, a little differently, but now, if you flip over the periodic table that was in the special folder, you should have this on the back. If you want to color code this to match the front, it's a great mnemonic device. And guess what? That's it for now. You should understand the blocks, how to use them to figure out which sublevels are filling, and how to predict characteristics and valence electrons. Go take your quiz.